Welcome back, everybody. So today we're going to play around with inverse functions, where we take a function and reverse its arrows. And we'd like to get a function back. So to start playing around, let's look at a few different functions here, and let's see what happens when we reverse the arrows. So with our first function here, we have a couple elements going to this first element and this last one going over here. We reverse the arrows. All right, we get two arrows like that. Another arrow like that. And so these arrows that we're getting, let's think of these as describing, at least right now, let's call it a relation F inverse. It may or may not be a function, but it's a way of kind of relating elements from one set to another. So in blue up here is what we get a function from B to A. And it's not, right? The issue is that this element here in B gets sent to two different things, and that's not allowed, right, if we want a function. Okay, well, what about our second function here? Well, now if we reverse the arrows, we don't have that same issue. So is what we have in blue here a function from B to A? Well, here the answer is also no. And the issue this time is a different one. The issue is that this element of B is left out of the party, right? If we want a function from B to A, well then every single element of B needs to have an arrow going out of it, needs to be associated to an element of A. All right, so because an element in B is left out, what we have in blue is not a function. All right, over here, we have another function. Let's reverse the arrows. All right, is what we have here a function from B to A? Yes, it is. All right. Everything in B has an arrow coming out of it, and nothing in B has more than one arrow coming out of it. And so we do get a function from B to A in this case. Now, but what's the difference between this third situation and these other two? Well, probably have noticed it's an issue of one-to-one and onto. Right? Our first original function f was it was onto, but not one-to-one, right? Because we had multiple things getting mapped to the same element, that broke our function when we reversed the direction of the arrows. Yeah, that's my dog in the background, if you can hear Heidi Pup. Our second function was one-to-one, but not onto. And that not onto messed us up. When we flipped the arrows, we had an element that was left out of the party. This third function is one-to-one and onto, right? It's a bijection, right? And that's the function that, when we reversed the arrows, gave us a legitimate function the other way. And I think it's believable at this point that this is the essential property that we need. That if we're going to get a function, when we reverse the direction of the arrows, that original function has to be a bijection. And that is a result that can be proven We're not going to go through the full proof. It's pretty, I don't know. It's very technical, but I feel like the payoff from it is just not worth it. We're going to play around with other proofs involving inverse functions, but not the following. We're just going to let these pictures kind of serve as the evidence in our minds of the following theorem. That if f from a to b is a function, then the relation given by reversing all arrows of f is a function f inverse from b to a if and only if f is bijective. All right, so if f is bijective, we get an inverse function. All right, if f is not bijective, then we don't get an inverse function. That's one way to think about this if and only if statement. All right, a little bit of terminology. In the situation when f is bijective, we say that f is an invertible function. It has an inverse. And we call this f inverse that we've described by reversing the arrows, the inverse function to f. All right, well, reversing the arrows, this is a very nice picture, an idea to have in mind. It's exactly the idea we want to have in mind. But to more formally and algebraically work with inverse functions, here's the definition. Right, if f from a to b is bijective, right, then f inverse from b to a is the function defined by f inverse of some b equals a if and only if f of a equals b. Right, the idea here, right, is if we have a and a b, well, if f gives us an arrow from a to b, well, then we're going to reverse that arrow for f inverse, and f inverse will send b to a. So this is the defining property of our inverse function. And so to start things off, let's look at a specific example. So let's let e be the set of even integers, set of all n in the integers such that n is even. Then I claim that the function half from e to the integers, defined by half of x equals x divided by 2, is bijective. We won't go through a very precise proof, but let's at least talk about a few points here. First of all, I think it's an interesting thing to think about. Are we actually mapping into z for any element of e? Right, we got division going on, and the integers are not closed under division, but right, if we have an even integer we're starting with, some 2 times k, well, if we divide that by 2, we'll get that k, right, which is an integer. So we are indeed mapping into the integers. So bijective, we need one-to-one and onto. The idea for one-to-one, right, well, if we assume that we have 2 inputs, let's say x and x1 and x2, they get mapped to the same thing. All right, so x1 over 2 equals x2 over 2. Well, multiplying by 2 is going to give us that x1 equals x2. All right, so that's a check. Right, again, not a formal proof here, but just the basic idea of what's going on with one-to-one. But what about for onto? Here, well, we'd want to let y be some integer. Apologize, I'm working with a mouse here. Bear with my handwriting. That says let. All right, we want to find an even integer that's going to map to our y that we picked out, well, how about 2y? Right, that's an even integer. 2 times some integer. And let me not write out, don't make me write half with my mouse. Let me say it like this. 2y gets sent to, all right, 2y over 2 through our function, which is y, the element that we chose. Check. All right, it's 1-to-1. It is on 2. Beautiful. It's a bijection, so it has an inverse. All right, so just a little bit of playing around here. Right, since half of 10 equals 5, right, 10 divided by 2, and half of 0 equals 0 divided by 2, which is 0, well, then we can make statements about the inverse function, right, just by flipping these input and outputs around, right? That's the game with our inverse functions. Right, if f of a equals b, well, then we know that f inverse of b equals a. So here, since half of 10 equals 5, we know that half inverse of 5 equals 10, and also half inverse of 0 equals 0. All right, pop quiz for you. What is half inverse of -8? If we'd like, we can think about this with a diagram here. All right, so half inverse, it's our pink arrow here. So we're wanting to know where it sends -8. Well, flip that around. We want to know where our original function, what our original function sends to -8. Right? Well, original function is half. Well, what number is half going to send to -8? Well, it's going to be -16. Right? It's going to send to -8. Or in other words, half of what equals -8? -16 gets sent to -8. And so half inverse of -8 is -16. All right. With the preview activity that you worked through for today, you had 2 functions in hand, and one of the things that you did was you looked at the composition of one and then the other, and then the opposite order as well. And what you probably noticed is whatever input you fed to one of these compositions, at the end of the day, you got that input spat back out. Right? The composition just handed you back what you plugged into it. Right? And that's going to be the game with inverse functions. Right? If we take an a, send that through f, and then f inverse, we're going to get sent back to a, and vice versa. If we start with a b, send that through f inverse, and then through f, we're going to get left with b. All right, this is kind of an intuitive idea. We're going to go through a proof. And this is going to be a nice example, along with some other proofs that we'll do tomorrow, of how we can take something that feels very intuitive and actually work with the definitions to prove. And this can actually be a paradoxically difficult thing to do, is take something that feels intuitive and actually work out a proof. Because we kind of just want to be like, well, of course. But no, we actually want to work with the definitions and show what needs to be shown. All right, so here we go. A couple statements here. If f from a to b is bijective, then, right, if we take any little a in big A, if we send that through f and then that through f inverse, we'll get our little a back. And similarly, if we take any little b in b, send that through f inverse and then through f, we'll get our little b back. Right, in the text, they work through this first result. I'll call it result A. We'll work through this second one, result B. All right, so to start off, right, let's assume the hypothesis. Suppose that f from A to B is bijective. All right, then what kind of statement are we trying to prove? Well, it's a for all statement, right? So to deal with that, we'll just let little b be a general element in big B. And then we just need to show that this right-hand equation holds. Well, how do we show that an equation holds? Well, usually we pick one side and just work with it. And through a series of manipulations, we show that we get the other side. Right? So usually we want to pick the more complicated side, and that's pretty clear which one is more complicated. We'll start on the left. All right, but before we do that, let's get sort of this, if I scroll up, this kind of A-B connection going on. Right? We've picked our general B. Let's, in our proof, introduce this A on the other side. All right, so to do that, all right, if we plug in B into our F inverse, we'll get some element of A, right, where F of A equals B. Right, this is just using the definition of our inverse function, right, that F inverse of B equals A, where F of A equals B. And with that introduced, we can now go ahead and start working with this left-hand side of the equation. All right, F of F inverse of B, well, we can take F inverse of B and swap that out with what it equals, A. And then F of A, well, that equals B. All right, so with that, we've verified our equation and have shown what needs to be shown. Now, I'd like to give a slightly different perspective on these two results here. That these are somehow telling us about two functions. So let's make a note that any set in the whole wide mathematical world always has an associated identity function. An identity, so capital I for identity, that maps from the set to itself, just defined by sending each and every element to that same element. All right, so to draw a picture, right, if this is A, we'll just copy paste A over here. So if we have X, Y, Z as our elements of A, and X, Y, Z, all right, the identity is just going to send X to X, Y to Y, and Z to Z. All right, that's how the identity works. Pop quiz. Earlier, we worked with the set of evens, E. What's going to be I sub E evaluated at negative 50? If you said negative 50, you are spot on. All right, that's how the identity works. Just sends an element to itself. Beautiful. All right. Well, what I claim is that our result up here is telling us that our two kind of compositions of our function and its inverse are actually giving us an identity function. Specifically, here's the corollary that follows from that theorem. So if f from a to b is bijective, then in the f inverse composed with f equals the identity on a, and that f composed with f inverse equals the identity on b. Now here, these equalities are slightly different than the ones up above, because these equalities are actually, these aren't just equalities of elements in a set, but these are equalities of functions. Right? And so to show that two functions are indeed equal, we need to check that they have the same domain, the same codomain, and the exact same output for each input that we send through. So since we worked with part B above, let's again look at part B down here. All right, and just work through the proof. It'll be pretty quick because of our work above. But let's think about each one of these in turn. All right, so supposing that f from a to b is bijective, let's consider where our two functions on the left and right are mapping. All right, well, the identity from b to b maps from b to b. And f inverse, right, that maps from b to a, and f maps from a to b, so this composition also maps from b to b. So note that f composed with f inverse maps from b to b, and the identity on b maps from b to b as well. All right, so the b to b and b to b, that gives us a big check for our same domain and codomain. All right, now to check that we have the same output for each input, well, let's choose a general input, something in big B. All right, so let's let little b be in B. And let's send it through our function. All right, well, first we'll send it through this composition on the left. All right, f of f inverse of little b. By definition of how compositions work, this is f of f inverse of b. And that equals little b, right, by our theorem above. Right, we showed that. All right, and also, just realized I forgot to write this on the page, so I'm going to scratch it in here. Also, if we send little b through our identity function, it'll hand us b. Therefore, or hence, that uses less letters. F composed with F inverse of B equals the identity evaluated at B and thus, make that T a capital, thus, all right, these two functions are equal. All right, oops, I forgot to erase that box. Then, that was dramatic. All right. All right, so the idea, sorry, this is really messy now, right? We send little b through our composition, saw what we got. We sent it through our other function, saw what we got. Hey, they're the same. Therefore, since our two functions have the same domain, codomain, and we just checked they do indeed have the same output for each input, they are equal as functions. All right, that's it for today. We'll play around with some more inverse function theorems tomorrow. Good work, everybody. I'll see you next time.